right? When it comes to mole concept, the basic terms that we need to know is that a substance is always categorized based on its physical and chemical behavior. Physically, they could be in solid states, liquids, or gaseous states. And chemically, when you categorize them, again, you have to see them into pure substances and mixed forms. Sorry. So that will be pure substances and mixed form. When I say pure substances, that could be an elemental form or molecules or in various compound form. Mixed form as in more like mixed salts, multiple salts mixed together. Now, general idea what we should have is every element and molecules are made up of atoms, and atoms will have protons, electrons, and neutrons. Now, when it comes to the term mole, mole is basically a number unit. Okay, just like a dozen, is a number unit. A gallon is a number unit, like that. So we have a number unit here. So number of entities of a substance in same as that of number of carbon atoms present in 1/12 of the mass of carbon 12 isotope. So if I take carbon 12 isotope, then 1/12 mass of that carbon 12 isotope, and the number of carbons present in it, that represents 1 mole of it. Correct? As per mass spectrography, we were able to predict what is the number of atoms present in it. Okay, theoretically, that if I take 12 grams of carbon 12 isotope, correct, you can see that 1/12 mass of if you notice 1/12 mass of carbon 12, that value of that value for 1/12 mass of the carbon 12 isotope was found to be 1.66 into 10 raised to power of minus 24 grams. Now, I could use this term that if this much is the mass for one carbon atom, isn't it? Then 12 grams of carbon would contain how many carbon atoms in it? Okay. And you can see the 12 and 12 will get cancelled here. So that makes it 6.022 into 10 raised to power of 23 carbon atoms. In simple terms, if we talk about 12 grams of carbon, it is equivalent to saying these many number of carbon atoms present in it. And this number is also referred as Avogadro's number. The same idea can be, extended to electrons, protons, any other species. Got it? So 12 grams of carbon is equivalent to these many carbon atoms. And mass of those many carbon atoms is equal to 12 grams. If you take the mass of 1 mole of carbon atom, so basically this is what we represent as 1 mole. Okay, we write this as 1 mole carbon atom. And if you refer to that 1 mole of carbon atom, correct? So that is equal to 12 grams. For example, if I ask you, find the mass of one carbon atom in grams. If I just ask you how many what is the mass of one carbon atom in grams? So what should come to your mind? That is, we know that the mass of Na carbon atoms, mass of Na carbon atoms is equal to 12 grams, right? So mass of one carbon atom will be equal to 12 by Na, right? This much will be in the grams value. So therefore, mass will be equal to 12 divided by Avogadro's number, which is 6.023 into 10 raised to power of 23. That is the number, Avogadro's number. As we calculate, it is coming out to be 1.996 into 10 raised to power of minus 23 grams. Okay, this will be the mass of one carbon atom. Got it? So in fact, you can relate the same idea to other elements also. Now listen, if I have to calculate the 1/12th mass of an carbon atom in grams, 1/12th mass of an carbon atom. Okay, so what does that mean? If I take 1/12th mass of carbon atom, we'll just learn that the mass of carbon atom is 12 by Na. So that means it is equal to 1 by Na. 1 by Na, if I do it, the value will be 1 by 6.023 into 10 raised to power of 23. And that value will come out to be 1.66 into 10 raised to power of minus 24 grams. This will be the mass of 1/12th of carbon atom, 1/12th mass of carbon atom. Now this unit is what will be useful going ahead, which we call it as 1 atomic mass unit, 1 AMU, atomic mass unit. And that is defined as 1.66 into 10 raised to power of minus 24 grams. Okay. It is also referred as 1U. U means unified mass. Unified mass. Everybody understood the term? What exactly is mole? Or how do we refer that in terms of mass of any other mass of carbon atoms? And how we can write that in terms of various terms like AMU, unified mass, Avogadro's number, and so on. Correct? Another general idea how I can give you about mole, right? This is one idea. The other idea of mole, I'll just try to give you another part of it. See, check out. Suppose if you notice the mass of one hydrogen atom, okay, mass of hydrogen atom. So I'm talking about only one hydrogen atom. This was found to be approximately 1.66 into 10 raised to power of minus 24 grams. So which is same as this number, right? Okay. So if I take, you know, uh, this is about one hydrogen atom here. So what if I have to take it as 1 gram of hydrogen atom? If I take it as 1 gram of hydrogen atom. So it is about just using this unitary method that for this much grams, it implies that there is one hydrogen atom. For this much grams, how many number of hydrogen atoms will be present? Therefore, number of hydrogen atoms present in 1 gram of hydrogen is 1 into, 1 divided by 1.66 into 10 raised to power of minus 24 grams. And this is 1 gram. So if I divide this again, I'll get this as 6.023 into 10 raised to power of 23, 23 atoms. So these many number of hydrogen atoms will be present if I take 1 gram of hydrogen atom. Okay. Now I'll give you one more crack of it. Another way of looking at it. So let's check out. Suppose if I talk about elements like nitrogen, oxygen, carbon, fluorine, all of them, we know their mass number. Mass number means number of protons plus number of protons plus number of neutrons. So mass number of nitrogen is 14, oxygen 16, carbon 12, fluorine 19, and so on. So if we have mass number as 14, so what has been noticed, right, using mass spectrography is that proton mass, one proton mass is approximately equal to 1.66 into 10 raised to power of minus 24 grams, which clearly suggests that the hydrogen mass and proton mass are no different because there is no neutron in hydrogen and the mass of electron is extremely negligible. So ignoring that part, one proton mass and one hydrogen mass is almost the same. And we got to also notice that one neutron mass, as per mass spectrography, is also very, very close to proton mass, which is slightly higher side, but still we can consider both of them are same. So one proton mass will be same as one neutron mass. In such case, if there are 14 protons plus neutrons, then mass of nitrogen atom will simply be mass of nitrogen atom will simply be 14 times of 1.66 into 10 raised to power of minus 24 grams. Correct? This much will be the mass of nitrogen atom. So this I'm representing as one nitrogen atom. So this is about one nitrogen atom. Correct? Now listen up carefully. Always try to convert this mass number in grams. Then what will happen? Check out. If 14 into this value is equivalent to one nitrogen atom, then 14 grams of nitrogen will be equivalent to how many number of nitrogen atoms? So therefore, number of nitrogen atoms present will be equal to 14 grams divided by 14 into 1.66 into 10 raised to power of minus 24. That again turns out to be 6.23 into 10 raised to power of 23 atoms. So in short, we could actually simply use the mass number and try to figure out what is the number of atoms present in it. All you need to know is what is the mass of a proton or what is the mass of neutron. In fact, you just need to understand this assumption that we can take them as same mass and calculate what are the number of atoms present in it. Okay. Any doubt in this page, please do let me know. Please check it out. Okay. In that case, that would be equal to 1 by Na. We learned this already. So this is the value which you will get. This for one unified mass. What if I write this in terms of kgs? 10 raised to power of minus 27 kgs. Okay. So again, you can see 1.66 into 10 raised to power of minus 27 kgs. If that represents one unified mass, okay, then how much will be that in terms of unified mass here? Correct? If this is one unified mass. So now if I take 50 kgs, then how many unified masses you will get? So that implies 50 into U divided by 1.66 into 10 raised to power of minus 27. Okay. Can I write this as 50U divided by 1.66 into 10 raised to power of minus 24? Correct? Into 10 raised to power of minus 3. I'm doing that because we know this number. That is 1 by this number is something 6.023 into 10 raised to power of minus plus 23. And that multiplied by now 10 raised to power of this value is 10 raised to power of minus 3. If that comes in the numerator, that will also become 10 raised to power of 3. That into 50. So which makes it, this I can approximate as 6. 6 into 50, here is 300 into 10 raised to power of 26. So which makes it 3 into 10 raised to power of 28 unified mass. That is how much you will be writing in terms of unified mass. Everybody clear? Or you can write this in terms of AMU. So 3 into 10 raised to power of 28 AMU. Okay.
I didn't
Okay.
quite get it after the 50U.
Hmm?
Could you just explain it again?
I said this much mass represents one unified mass of any substance, just one unified mass, correct?
Yeah, yeah.
Then 50 kgs represent how much unified mass? This
50,
50 into 1u divided by this number, right?
yeah,
So that's what I have solved. This number, you know that
6.
1.66 into 10 raised to the power of minus 27 is nothing but 1 by Avogadro's number.
Yeah,
So 1 by this number is same as Avogadro's number, which is this one.
yeah.
That into 50 into 10 raised to the power of 3. After calculating, I'm getting this many unified masses.
Hmm.
Okay, beta?
Yeah.
Right. Now let's understand another important term here. What is relative atomic mass? Okay. So this will be pretty useful. It is about the mass given of an atom. What is the mass given by an atom? Divided by 1/12 of mass of carbon 12 isotope. Okay. So mass, what has been noticed, what has been identified is if I take mass of one atom, suppose if at all I take mass of one atom, right? I'm talking about the mass or weight of one atom. That divided by 1/12 mass of carbon 12 isotope, you would get a simple integer number in most cases. In most cases, you'll get a simple integer number. And that integer value always matches with the atomic mass or mass number. Okay. Therefore, if you know the mass number of any element, this is just the trick which I have applied here right now, right? If you just know the mass number of a particular atom, you just need to multiply that with 1 AMU. This is that 1 AMU, and you will be able to get what is the mass of that atom. And that is what is useful with relative atomic mass. So mass of any unknown atom is equal to RAM, relative atomic mass of that atom Z, into 1/12 mass of carbon 12. And 1/12 mass of carbon 12 is what we defined as one unified mass or one AMU. Okay. And since this is grams by grams, so RAM is dimensionless. Okay. And it will always match with the value of it will always match with the value of mass number in most cases, except if you notice the case of copper and chlorine. In most other cases it will always match with the mass of an mass number of an atom. Okay, so these are all relative atomic masses. To be precise, this is not exactly 1. It is supposed to be 1.008. Okay. And here also this is 4.00. This is 7.001, like that. One second. Check. So like that, if you take oxygen, for example, it is 16.01, like that. So I've ignored that decimal ones. So that makes easier to remember that if this is the relative atomic mass, just multiply that with the AMU value, you will be able to get what is the mass of an atom. Okay. Check this out. If I were to calculate the number of moles that are present in 0.24 grams of carbon, I want to calculate number of moles present in 0.24 grams of carbon. Okay. And also find the number of moles in 6022 atoms. And also calculate the mass of 6022 atoms present. So what are all the what is all the calculation I can do? Check out. I know that 12 grams implies 1 mole of carbon atoms. So 1 gram implies 1 by 12th mole of carbon atom. So if 0.4 grams is taken, that means 0.4 into 1 by 12th of moles. So the answer is 0.02 moles. So using this analogy, I can formulate a simple formula here. That is, if I want to calculate the number of moles of any species, I would simply use their mass, what is the given mass of the species, upon what is the molar mass or the atomic mass. I can use the term molar mass or atomic mass of the species. Okay. And what is that atomic mass in this case? For example, 12 grams. 12 grams is the atomic mass of carbon. Okay. That is the mass which 1 mole of that atom consists of. Correct. And next, number of moles of species can also be written as number of the particles given or number of the species particles given divided by Avogadro's number. That will also yield you number of moles. Hence, these are the number of atoms given. So number of atoms divided by Avogadro's number, that defines these many moles. Similarly, based on this, I could generate like a formula that number of moles is equal to mass, right? Mass by molar mass or weight by atomic weight, anything. So therefore, I can write weight of an atom or weight of a substance is equal to number of moles into molecular weight. So this can also be used as a formula whenever you have been given, you have to find out an unknown amount of mass. Check out. If I have to calculate the mass or weight of a substance, it is number of moles into molecular weight. So number of moles, we just got it as 10 raised to power of minus 20 into molecular weight is 12. So that turns out into mass. So 12 into 10 raised to power of minus 20. Okay. Or when you write it in grams, typically this is called the scientific notation. In scientific notation, we try to keep the number of significant figures to only 1 before the decimal. So it is 1.2 into 10 raised to power of minus 19 grams of carbon. Okay. I hope you guys understood this stuff. What is number of moles, how it is defined in terms of the given mass. Now notice, we have learned this term isotopes before, but let me remind you, an atom of an element having same atomic number but different mass number. Okay. Atomic mass, or what we call it as mass number. That is called as isotope. For example, sodium's relative atomic mass is 23. That 23 number, if you decode, it is coming from the fact that there are 11 protons, 11 electrons, and 12 neutrons. So 11 electron mass is ignorant. It is only proton and neutron mass that we need to consider. Why is that so? See, mass of an electron is approximately 9.1 into 10 raised to power of minus 31 kgs. Or if I write that in terms of grams, it is 10 raised to power of minus 28 grams. On the other hand, mass of a proton and mass of a neutron are approximately 1.66 into 10 raised to power of minus 24 grams. If I compare them, mass of proton is approximately 1836 times that of mass of electron. So which is huge, right? Almost 2000 times greater than that of mass of electron. That's the reason why we ignore the electron mass contribution. So now it is the proton mass and neutron mass together. So multiply that. After doing that, you can see it is coming out to be 23 times of this number, and this number is nothing but one unified mass, or 23 AMU. Okay, 23 AMU. Clear? So see, mass of an atom can always be written in terms of relative atomic mass, which is nothing but number of nucleons. Nucleons is a word used which implies number of particles in nucleus, which is number of protons plus number of neutrons. Okay, and that is represented as A. Okay, and Z is atomic number, which is number of protons. So here you can see Z is atomic number, which is number of protons, and A is mass number, which is number of nucleons. Right? Check out. This is a typical notation for an element. We always write A here and Z here. A is the mass number, Z is the atomic number. And when it comes to hydrogen, the atomic number is same, but the mass number is changing. So these three species of that hydrogen is what we call it as isotopes. See, you can see there are all three will have same number of atomic number, but different number of mass numbers, right? So which is number of neutrons are different here. Okay, the one which has two neutrons we call it as tritium. The one with one neutron, it is deuterium. Zero neutron is protium. Got it? So what happens here? See, why earlier I told you that chlorine and copper has a different relative atomic mass, because it has a fractional value. Why is that so? Because whenever we are trying to figure out the mass of a substance, you have to take the average mass of all the isotopes. So, for example, if I take chlorine, chlorine exists in two forms. That is chlorine 3717, chlorine 3517. Okay, in which it has 25% biomass of this substance, 75% biomass of this substance. So if I take the average, that is 25% into 37 as the mass number, 75% into 35 as the mass number here divided by 100. This is the weighted average. So when you notice the weighted average, you are getting it as 35.5 unified mass. That's the reason why the relative atomic mass of chlorine, we call it as 35.5. Got the point? Okay. Therefore, if this is about only two isotopes, there could be multiple isotopes like this. That's why the average atomic mass of a substance can be always used with this formula, that A1, which is the mass number, into X1 is the percentage amount. So A1 X1, A2 X2, A3 X3, and so on, all of that divided by 100, or sum of this, right, divided by 100. So that will give us atomic mass. Okay, average atomic mass. Correct. This average atomic mass, in this language we also call it as, abundance. What is the abundance of certain element or certain species? Correct. So occurrence or abundance in percentage weight of this isotope. So that is what we will be writing here. Clear? Okay. So suppose if you have atomic mass, average atomic mass of an element, and instead of giving percentage mass contribution, if at all I give you how many moles are present, so I can always use this as A1N1 plus A2N2 plus A3N3 and so on, divided by N1 plus N2 plus N3. That will give the average atomic mass. Okay. Clear? Right. So use this idea to calculate the uh, answer here for this question. Suppose there is an element X and it's showing three isotopic forms, 12, 13, 14, with an abundance of 80, 15, and 5 percentage. What is the average atomic mass? Okay. So how do we do that? So that is equal to average atomic mass is equal to 12 cross 80 plus 13 cross 15 plus 14 cross 5 whole divided by 100. Got it? That's coming out to be 1238 divided by 100. So which is 12.38. So that is the average atomic mass of that element X. Clear?
Yes, sir.
Right, sorry, 2.5. I'm getting 2.5 minus. Right. Next. Notice this one. 0.81 grams of aluminum is given. I need to find out how many moles it has, how many atoms it has, how many protons, how many neutrons, how many electrons. Is the question clear? I can help you with the representation of aluminum. Aluminum is 2713. This is the representation of aluminum. Okay. So using this particular representation and the data, you have to answer all of this. All right. So try it out. Give me an answer. They how about next one, beta? Atoms.
Sir, 0.03 into Na, Avogadro's
Very good.
number.
So number of atoms of aluminum is equal to 0.032 into Avogadro's number. So 6.023 into 10 raised to the power of 23. Okay. So approximately, if at all I take it, so that is 0.18 into 10 raised to the power of 23, or 1.8 into 10 raised to the power of 22. This is the scientific notation. Okay. Next. See, Kapil, give me an answer, beta. Number of protons.
Number of protons, um, same as this Avogadro, the 1.8 into 10 raised to power 2.
This one.
Yeah, same as the B also.
But these are about number of aluminum atoms, no, beta. Atoms, these are
Oh,
aluminum atoms.
oh, so
So,
it's a mm,
so number of protons will be number of aluminum atoms multiplied by each atom has how many protons?
is
30.
30.
Correct. So you just have to multiply that with 30. Okay. So that I'm getting it as 23.4 into 10 raised to the power of 22. So how do I put it in scientific notation? 2.34 into 10 raised to the power of 23 protons. Right, beta? Right. Manav, how about neutrons, beta?
2.52 into 10 raised to 23.
2.5,
2.
2.52.
Yes, sir.
Right, 2.52. Very good. So number of neutrons is equal to 2.52 into 10 raised to the power of 23. It's just a multiplication of that part. Okay. Number of electrons will be same as that of protons. So number of electrons will be same as number of protons, which is equal to 2.34 into 10 raised to the power of 23 protons. Got it? Now, the same question, but this time I'm using, instead of aluminum, using Al plus 3. So what does that change? What are the factors that will change? Anything that changes here?
Number of electrons.
That's it. Only number of electrons. Rest all will remain the same, correct? So let me just write down that. Okay. A, B, C, D remains same as above, but number of electrons change. So how many number of electrons will be present now? Check. If it is Al plus 3 suggests that it has lost 3 electrons. So number of electrons currently we have is 10. So therefore, number of electrons in total, capital N and E, number of electrons will be equal to number of moles of Al plus 3 multiplied by 10. How many moles you will have? 1.8 into 10 raised to the power of 22, which we already got, into 10. So which is 1.8 into 10 raised to the power of 23 electrons. Is this part clear? Everybody? Right. Right. So this is about the basic idea regarding the mole, and you can go through the assignment. I have already uploaded the assignment, uh, the module for this topic. You can go through that and start solving the questions, whichever that is related to mole. Now let's extend this idea to chemical reactions. If you are measuring the chemicals based on the mole ratios in a chemical reaction, then we call it as stoichiometry. Okay. In stoichiometry, the first part that you need to understand is how to read a reaction. A chemical reaction that is written is always read with respect to its coefficients present on it. Now, this A, B, C, D are called as stoichiometric coefficients. And we read a reaction based on those coefficients. That is, if I have, let's say, small a moles of A reacting with small b moles of B, right? It will form small b moles of C and small d moles of D. That's how we read the reaction, correct? And we read that considering that the reaction is balanced. That means whatever the number of atoms present on the left hand side and whatever the atoms that are present on the right hand side, they both appear same. Got it? Just a second. Right, sorry. Check. So next part is about reading out the reaction. We just learned how to read the reaction. Check out. Generally, molecules are of two kinds. Homoatomic molecules are heteroatomic molecules. If only one type of atom is present, we call it as homoatomic molecules like this O2, N2, P4, and so on. And then we also have heteroatomic molecules, which is like two combination of two or more than two combination of atoms. Next, we need to understand the term atomicity. Atomicity is the number of atoms present in a molecule. Now that molecule could be homoatomic or molecule could be heteroatomic. So for example, if it is O3, atomicity is 3, while if it is ethane, atomicity is 8. Okay. Now, before judging into how to apply it in stoichiometry, we need to realize how do we write the molar mass of the molecules. Got it? Based on their atomicity, we should be able to write what is their molar mass. I gave you a hint earlier that whenever we use the number of protons, or sorry, number of uh, protons and neutrons together, which is mass number, and convert that mass number into gram, right? Then the number of particular atoms present in it will always be equal to Avogadro's number, or which is 1. And that's exactly what we are trying to do here also. Molar mass can be written in terms of two things, guys, everybody. Either in terms of AMU, or we simply write in terms of grams. Correct? If you're writing directly in terms of grams, we use the terminology gram molecular mass. Gram molecular mass. Okay. So you can see basically that means, what does that mean? I can say 1 mole of HCl consists of 36.5 grams in weight, which is 1 gram of hydrogen. plus 35.5 grams of chlorine. Make sense? This 35.5 is the relative atomic mass number. 1 is the relative atomic mass number, relative atomic mass of hydrogen. And this is for chlorine. So you just put that in grams, you will get this in moles. Similarly, here also, when I say 98, that means I am taking 2 times of 1 gram of hydrogen plus 1 time of 32 grams of sulfur plus 4 times of 16 grams of oxygen. And that adding all together, we will get this as 98 grams. Correct? So now you can see up to this numbers here, you can see all this 7 here, 6 here, and 6 here, right? So these are most commonly asked molecules, right? So you should be able to figure out quickly what is their atomic number, what is their molecular mass or gram molecular mass. So I guess all of you got this, how to do that, right? Now, given the molecule here, for example, if you have 0.45 grams of H2C2O4, okay, then we need to figure out all of these details for one particular case, like H2C2O4. If you have 0.45 grams of H2C2O4, to relate that to number of moles, we know that number of moles can be done calculated as weight by molecular weight. So what we require here is the molecular weight of H2C2O4, which is nothing but oxalic acid. Okay, I think I've already written the oxalic acid here. I can take it that from the data, which is 90. Okay, so molecular weight of oxalic acid is 90. So my request is now, please check this out and try to figure out all these terms. Everybody, check it out. Done. A to I. Try it out. Try them out. Yes, Kapil. Let's go one by one. Right. Check out. First one is 0.5 divided by 90. Correct, isn't it? So that comes to be 0.02 moles. Okay. Next. What are these gram molecule means? Okay. Let me tell you what are this term means. See, first one is 0.02 moles. Now see the second term. What is gram molecule means? Gram moles or gram molecules is how much is the uh, moles of atom in represented in grams. Moles of atom when represented in grams.
So 0.05, right?
Represented in grams. Or beta 0.2, sorry, 0.05. Yeah. Right. See, moles of atom when represented in grams. That is, for example, if I say this as 12 grams of carbon, the same thing I can also write it as 1 gram atom of carbon. Is that point clear? Similarly, let's say if at all I write this as 32 grams of oxygen, O2. So I can write this as 1 gram molecule of oxygen. Correct? So this is an alternative name for mole. That's all. Gram atom or gram molecule is an alternative name for mole. Okay. So you can see number of gram moles here. So gram moles here is same. So that is 0.05 moles. Gram molecules, because we are talking about molecules only, that is also 0.05 moles only. Okay. Number of molecules now. Number of molecules, how many we will have? 0.05 into Avogadro's number. So which is 0.05 into 6. I'm writing it in approximate value. So into 23. So that makes it 0.3 into 10 raised to power of 23, or 3 into 10 raised to power of 22, okay, molecules. Number of atoms, see, if these are the number of molecules we got, 22 molecules, and in that molecule, how many atoms do we have? Count it out. 4 plus 2 plus 2, total 8. One molecule has 8 of them. So therefore, 2.4 into 10 raised to power of 23 atoms. These many number of atoms we have. And number of oxygen atoms, specifically oxygen atoms, how many we have? Only 4. So again, I will multiply the same thing, 3 into 10 raised to power of 22 into 4. So which is 1.2 into 10 raised to power of 23 atoms. Next, gram atoms of oxygen. Gram atoms of oxygen means how many moles of oxygen, right? So gram atoms is referring to moles. So how many moles of oxygen? Because we know that one molecule, how many moles of molecule we have? 0.05 moles. So I can write this as 0.05 moles into 4. So which makes it 0.2 moles of gram atoms of molecules, gram atoms of oxygen. Now check out number of electrons, everybody. So to find the number of electrons, first we need to check out each atom how many electrons it has. H2, C2, O4. You know that every hydrogen has one electron, so that makes it 2 here. Every carbon has 6 electrons, and every oxygen has 8 electrons. Okay, so that makes it 2 plus 12 plus 32. Correct? So how many we have here total? 46. So 46 electrons present in 1 mole. So 1 mole is how much here? I mean, we got 0.05 moles here. Correct? So that makes it 44. Here. So 46 into 0.05. So that is 2.3 moles. Okay. Similarly, number of neutrons. How many neutrons do we have? So let's count that as well. If you may notice that number of protons and number of neutrons will be same in the case of carbon and oxygen. Nitrogen has 0. So when it comes to nitrogen, we have 0 neutrons. When it comes to carbon, we have 2 into 6 neutrons. When it comes to oxygen, we have 4 into 8 neutrons. Okay. So that makes it 12 plus 32. So how much we have? 44. So 44 into 0.05. Correct. So which is 2.2 moles. Okay. So if you write in terms of moles, it is okay. Or I can write it as 2.3 into Na, or 2.2 into Na, Avogadro's number. Right. So that will give you the total number of electrons. Is this point clear, everybody?
Yes, sir.
Nitya, any doubt?
No, sir.
Kapil?
No, sir.
Manav? Right. I would suggest you to try this question now. Identify minimum molar mass of a compound. Please do this question. We need to calculate what is the minimum molecular mass of this proton. Okay. Okay. So, if you have 100 grams of protein, okay, 100 grams of protein, that does contain 0.2 grams of nitrogen. Okay. So if I take 14 grams of nitrogen, because minimum molar mass implies that I should have at least one nitrogen. Okay. So therefore, weight of protein, right? Sorry, molecular mass of protein, molecular weight of protein will be equal to 100 into 14 by 0.2. correct? So that is 7,000 grams per mole. Okay, so that is the molecular mass. Clear? Do the same thing in this. Try the next one also in a similar style. Okay. Okay. If hemoglobin contains this much amount of iron, right, by percentage, then calculate number of iron atoms present in one molecule of hemoglobin. Molecular weight of hemoglobin is given. Please check. Right there, that's correct. Others, finish it. Because others must have got the earlier question. So you can see if you have 100 grams of hemoglobin, it does contain 0.33 grams of iron. This much will be iron present. Okay. And now you have been given the molar mass as 70,000 grams. So for that, how much will be the mass of iron present? So mass of iron present in it would be 70,000 into 0.33 upon 100. Correct? So that is 700 into 0.33. Correct? So that is nothing but approximately 700 into 1 by 3. Now, notice atomic weight of iron is 56. Okay, that will be usually given to you, don't worry. Okay, so therefore, number of atoms of iron present in it would be mass is 700 into 1 by 3 divided by 56, correct? Right? So therefore, that is equal to 700 by 3 into 56, which is approximately 4. Got it? So this will be the number of iron atoms present. Clear? Right. Check out. Minimum molar mass
Can
of
you
a
show?
compound which
Sure.
consists of what, beta?
Can you just show the last page again?
Yeah, sure. Please check.
Yep, thank you.
Let's go to the next one. Calculate the minimum molar mass of a compound which contains 40% of carbon and 20 by 3% of hydrogen. Calculate quickly. So when the percentage weight is given, you calculate the number of approximate atoms what you can get. That is mass divided by atomic mass. Here also mass divided by atomic mass. Okay. So this value is coming out approximately 3.66 and this is coming out to be 6.66. Got it? Then take the simple ratio of these two, which means divide by the smallest number between these two. So smallest number is 3.33, right? And here also 6.66 by 3.33. That gives us simplest ratio, which is 1:2. So C1H2 is the lowest or the minimum molar mass which you can have, which is also called as empirical mass. It's called as empirical mass. So empirical mass is 12 plus 2, which is 14 grams. Done? Done? Now let's understand the next term, which is Avogadro's law. There are two important laws here. So first is Gay-Lussac's law, and that is and then the extension towards Avogadro's law. According to Gay-Lussac's law, the volume proportions of the reactants and products will be same as their mole proportions, which means imagine there is a reaction that is happening like this: N2 plus 3H2 giving 2NH3. Well, if you read it in terms of moles, it meant that we have 1 mole of nitrogen reacting with 3 moles of hydrogen to give 2 moles of ammonia. Correct. This is in terms of reading in terms of moles. Now, as per Gay-Lussac's law, if all three are gases, right? If all three are gases, we can read that equation in terms of volumes as well. That is, 1 volume of nitrogen reacts with 3 volumes of hydrogen to produce 2 volumes of ammonia. So this is the way we can read it. Clear? Okay. So check. And now, when you compare something as an ideal gas is a gas where there are no molecular interactions between the particles. And typically for any calculations, any parametric calculations like pressure, volume, temperature, generally we assume the gases are ideal. Okay. So imagine if I give an ideal gas will always have a validation in terms of this ideal gas equation, which is pressure into volume is equal to nRT. How do we prove it and all? We'll see in the next topic. Here we just need a formula. Okay. So PV is equal to nRT. So P represent pressure of the gas, V is the volume of the container, okay, and N is the number of moles, and T is the temperature. Okay, just a second. Sorry, check. Now, if temperature and pressure of a gas is constant, if it's not changing, right? In that case, the volume is directly proportional to number of moles. And the Gay-Lussac's law is validated considering this point that volume is directly proportional to number of moles. Now, there are two types of conditions that we will take. One is STP, known as standard temperature and pressure condition, where the volume of a gas occupied by 1 mole is equivalent to 22.4 liters if pressure is 1 atm and temperature is 273 kelvins. Or it is 22.7 liters if pressure is 1 bar and temperature is 273 kelvins. Correct? And STP and NTP are generally interchangeable, but most of the time we will relate this value to NTP in the questions and this value to STP in the questions. Okay. So, for example, if I give you a question like a gas mixture contains this many grams of carbon dioxide, rest is argon, hydrogen, and oxygen, nitrogen, and so on. And I need to figure out what is the final volume of the mixture of those gases. So what would I do? First, I will try to convert everything into moles. So number of moles of carbon dioxide will be 44 divided by 44. Why? 44 is the molar mass of carbon dioxide, which makes it 1 mole. Likewise, number of moles of argon. If you notice number of moles of argon, it is 1.2 grams divided by argon's what do you say? Argon's molar mass is 40. Correct. Next, if it comes to number of moles of hydrogen, so that is 8 divided by 2. Why 2? Because atomic molar mass of hydrogen gas is 2. And next, notice this one, 2 gram molecules of O2, right? So number of moles of O2 is same as number of gram molecules of O2. gram molecules of what? I told you this earlier with the definition. So therefore, we have 2 moles here. And next, number of moles of N2 gas. Now, he has given here as 2 gram atoms of nitrogen. So, you know that there are 2 moles of nitrogen atoms. Can I say that 2 gram atoms of nitrogen is equivalent to writing it as, 2 moles of nitrogen atoms. And 2 moles of nitrogen atom is equivalent to writing 1 mole of nitrogen gas. 1 mole of nitrogen gas. Therefore, number of moles of nitrogen gas is 1 mole. Okay. Now, let's put all together and write number of moles of mixture, which is equal to 1 plus 1.2 by 40 here,
0.03.
0.03 plus 4 plus 2 plus 1. So this is the final value of number of moles. So how many we are getting, beta? 4, 6, 7, 8. Okay, 8.03. 8.03. So now if I want to calculate what is the volume occupied by the gas mixture, it will be 22.4 into 8.03 at NTP. Okay, so 22.4 into 8.03. So that is 179.8 liters. Okay. So I hope this part is also clear, everybody. So if we have a mixture of gases, we just identify everything in moles and we can relate that using Gay-Lussac's law. Okay, that we can always reach the volume and moles in a similar ratio. Done? Right. Shall we go ahead? Nitya, any doubt here, beta?
So,
Let's see. Sorry, one second. If it comes to densities, when it comes to densities, there are two terms that we need to check. One is absolute density, other one is relative density. Absolute density is absolute mass of a substance by volume. Relative density are of two kinds. One is specific gravity, other one is vapor density. Specific gravity is density of the given substance, absolute density of a given substance, divided by density of water at 4 degrees Celsius. At 4 degrees Celsius, density of water is 1 gram per ml. And next is vapor density. Vapor density is also defined as a reference density here, which is density of any particular gas divided by density of a reference gas. Usually, that reference gas is always taken as hydrogen gas. Okay, but both should be maintained at same temperature and pressure while measuring the densities. Okay, so this is what by definition is. So now let's check it out. Specific gravity is gravity is dimensionless. Magnitude, it is just the magnitude of density of a substance. So if it comes to vapor density, dimensionless. Vapor density of a gas is density of a gas by reference, and which is equal to density of gas by density of hydrogen. And see, if you know PV is equal to nRT is valid for any ideal gas, can I write this volume term? I mean, if I take this volume term to the right hand side, it will become weight. If I take it to the right hand side, this number of moles, I'm writing it as weight by molar mass, and I'm taking this volume to the right hand side. So then what do I get here is weight by volume, sorry, on one side, and molar mass, if I pull it to the pressure side, I'll write it as P cross M is equal to W by V into R into T. Correct? So we know that W by V is nothing but density that into RT. Now PM is equal to dRT. So density of a gas can be written as PM by RT. So this is another way of representing the ideal gas equation in terms of density. That is, density of a gas is PM by RT. So from here we can write density of a gas is directly proportional to its molar mass. So if I calculate vapor density of gas with respect to hydrogen, it should be density of a gas by density of hydrogen, which means molar mass of a gas by molar mass of hydrogen. Because pressure and temperature terms are anyway same. Hence, molar mass of hydrogen gas is 2. Hence, vapor density of any gas can be written as molar mass by 2. Okay. So keep that in mind. So vapor density of a gas is simply molar mass by 2. Okay. What if I have to find out the density of a mixture, correct? Of the density of a gas mixture. Let's say there are gas A, B, C, and I need to find out what is the density of the mixture of these gases. Then what I can write? I can write it as pressure into molar mass of the mixture of the gases divided by R into T. Now the challenging part is how to calculate molar mass of the mixture. See, molar mass of a mixture of gases can be always written as weight of the mixture of gases divided by number of moles of the mixture of gases. Why? We know the formula that number of moles is weight by molar mass. So molar mass will be simply weight by number of moles. Okay. So we can use this term. So I can write molar mass of a mixture is equal to weight. Achha, how can I write the weight, beta? Weight of an individual substance can be written as molar mass of that substance into number of moles of that substance. Correct? And that's what we can do. If A is a gas, B is a gas, and C is a gas, I can write number of moles of A into molar mass of A plus number of moles of B into molar mass of B into number of moles of C into molar mass of C. So this defines the weight of A, weight of B, and weight of C. So sum of these three will give you mixture weight divided by total number of moles is number of moles of A plus B plus C. Okay. Now here I'm defining a new term known as mole fraction. What is mole fraction? Mole fraction of a gas, okay, is how many number of moles of a particular gas is with respect to the total number of moles of gases. This is mole fraction of a particular gas. In this case, I'm referring the gas as A, so molar mass of A. I mean, mole fraction of A. Hence, molar mass of the mixture is equal to summation of all the gas products here, that is number of moles into molar mass product, divided by summation of all the moles. So that gives you molar mass of A, mole fraction of A into Ma, mole fraction of B into Mb plus mole fraction of C into Mc. Okay. So this way, molar mass of mixture can be calculated. So once you know the molar mass of the mixture, substitute that here, you can calculate what is density of the mixture. Got it? Use that simple logic and calculate the next term here. Check out what is the percentage mass of oxygen in air having molar mass is 29 gram per mole. That is the molar mass of air. Try it out. Okay. So I hope you guys got that. It has 25 percentage and 75 percentage. This is for O2. This is for N2. Okay. Yeah. So we can simply calculate the mole fraction first and then figure out what is the amount. Okay. So that is mole fraction of O2 into 32 plus mole fraction of N2 into 28. That will be equal to 29. Okay. Okay.
అన్నం తింటలేదు సార్ ముక్కలే తింటున్నా
Sorry guys, check. So we can write this as x here into 32 plus 1 minus x here into 28, that is equal to 29. Okay, so keeping that, you can calculate x, you will get this as 0.5. So percentage oxygen would be 25%. Done. Use the same similar idea and try the next one. We have density of ClFX, which is 0.4625 gram per liter, and density of hydrogen gas is 0.1 gram per liter at same temperature. Find the value of X. Okay, clear? Check out what is the value of X. Just use the vapor density analogy here. You'll be able to do it. You know that vapor density is relative densities. Use the idea of relative densities and calculate. So check it out. So what do we have here? So vapor density of gases can be written as density of a gas divided by reference density. In this case, it is hydrogen. And if I do that, you will get this as same as molar mass of a gas upon molar mass of hydrogen gas. So what I can do here is density of a gas, which is 0.4625 upon density of hydrogen, which is 0.01. That is equal to molar mass of a gas. In this case, 35.5, which is the atomic mass of chlorine, plus X times of 19, which is the atomic mass of fluorine, that divided by hydrogen, which is 2. That's all we need to solve. Okay. So after solving, I'm getting X is equal to 3. Clear, guys? Nitya, Kapil, any doubt here?
No, sir.
No, sir.
Right. Try this one also in a similar way. Carbon, hydrogen, nitrogen are given in this ratio, mole ratio. We need to, sorry, mass ratio. This is mass ratio. We need to calculate what is the vapor density of given vapor density. We have to calculate empirical formula and molecular formula. What will be the formula of that compound? Try it out. I was getting empirical formula. First, I was getting empirical formula as C3H4N1. Okay, so which makes empirical mass as 54 grams per mole. Okay, correct. Which is what is the vapor density given. And molecular formula is C6H8N2. Okay, so all you need to do is just take out the ratio in terms of weights. That is, weight of carbon is some 9x, weight of hydrogen is 1x, weight of nitrogen as 3.5x. And then find out number of moles of nitrogen, 9x by 12, and here it is x by 1, and here it is 3.5x by 14. Correct? Now take out, this is the smallest value here. So for that, you have to divide it here. Sorry, nitrogen is the smallest value here. So that you divide it by hydrogen as well as by carbon. So approximate closest values you will get here is 3, 4, and 1. So that becomes the empirical form. Correct? And since you notice that the empirical mass and vapor density are matching, that means molecular weight will be 2 times of vapor density. We learned that vapor density is molecular mass by 2. So that has to be 54 into 2, correct? So which means the molecular formula should be just double of that of empirical formula. So that is the formula part. Okay. I guess this part is clear.
Yes.
Now let's understand the term what are limiting and excess reagents. Okay. For example, if I have a chemical reaction and you know how to read it, A, B, C, and D are moles. These are reactant moles. These are product moles. Imagine if I give the initial initial moles of A as A naught, initial one second. Sorry. So A naught are the number of moles of A, B naught are the number of moles of B. So out of this A naught, imagine during the set of reaction, some X moles have been consumed, X moles have been reacted. Then how much moles of B will be reacted depends upon their ratio. That is, for A moles, if B moles are being supposed to be consumed, then for X moles, then Bx by A mole should be consumed. So B naught minus Bx by A are the number of moles that will be consumed. So this will be the leftover number of moles, and this will be the leftover number of moles of A. And Cx by A are the number of moles formed here, and Dx by A are the number of moles formed here. That is again based on the A to C ratio and A to D ratio. Okay. So every time a reaction happens, it will go in this way. Okay. So now, if at all I take a mole analysis here, I can say that X by A, Bx by A, Cx by A, and Dx by A. Correct? So this is the ratio which we got in all these cases. Correct? So Bx by A, Cx by A, Dx by A, and this is X by A. I mean, of course, for A moles, if X moles is consumed, for 1 mole, X by A will be consumed. Okay. Now, what if there is certain amount of ratio that is mismatching? That means if I take the A value, I mean some A naught value here, I'm expecting some value of B here, but that is mismatching. In such situation, we will start having something called limiting reagent and excess reagent. See this scenario. Suppose I have 80 grams of magnesium and I'm reacting that with 32 grams of oxygen. I need to find out how much is the final MgO forming and figure out if at all there is any limiting reagent or excess reagent present. See, the reaction goes like this. Magnesium ribbon burns heavily in oxygen to form magnesium oxide. This is a very standard combustion reaction. First thing we need to do is balance that reaction. So how do I balance it? You can see I can make this as half of O2 here. Now, the number of atoms on the left and number of atoms on the right are balanced. Then what I'll do, the given mass, I will try to convert into number of moles. So number of moles of magnesium would be 80 by 24. 24 is the molar mass, atomic mass of magnesium. And number of moles of O2 will be 32 by 32, which is 1 mole. Got it? Clear? So, if you see, we have this as 1 by 3 moles here. Correct. Okay. Sorry. 10 by 3. 10 by 3 moles here. So, I have this as 10 by 3 moles of magnesium and 1 mole of oxygen. This was given. This is the given amount. Now, what is expected? If at all I have 1 mole of magnesium, half a mole is required. correct? Half a mole is required. But what if I have, what if I have 10 by 3 moles? For 10 by 3 moles, how much is expected here? So 10 by 3 multiplied by half. So which makes it 10 by 6 or simply 5 by 3. Clear? So I'm expecting 5 by 3 moles. 5 by 3 moles is greater than 1 mole, which means I have given less amount of oxygen as per ideally what is required. Okay. Since the quantity given is less here, this will become limiting reagent. If O2 becomes limiting reagent, the magnesium will become excess reagent. Now the entire reaction is driven only on the basis of oxygen and not on the basis of magnesium. Hence, if I say 1 mole, so if I say this as half a mole requires 1 mole of magnesium, then 1 mole requires how much? So 1 mole requires 2 moles, right? So because half requires 1, so 1 requires 2. Therefore, out of 10 by 3, 2 moles will be consumed. So rest will be leftover mass. So left moles will be equal to, so 4 by 3, correct? And here nothing will be left. Everything is consumed. And now the amount of MgO formed will only dependent on how much limiting reagent has been consumed. Hence, for 0.5 moles, if 1 mole of MgO is forming, so for 1 mole, how many moles will it form? It will form 2 moles. So we can say that 2 moles of MgO is formed. 2 moles of MgO is formed. Therefore, from here I can write the weight of MgO will be equal to 2 moles into molar mass. Got it? Which is 40. Clear? So how much is the molar mass? How much is the weight now? 80 grams. Got it? So we'll get this as 80 grams of MgO here. Okay. And how much is the magnesium left over? Magnesium left over will be 4 by 3 moles multiplied by atomic mass is 24. Correct? So that makes it 32 grams left over. So 32 grams of magnesium is left over and 80 grams of Mg is formed. Clear? And see the mass ratio also, everybody. How much is the mass I took? I took initially 80 and 32. Now how much is the mass, that is total mass? 80 plus 32. So you can see the mass is conserved. So I hope you understood the logic, guys. How to use the limiting reagent.
Yes, sir.
Good. Apply that to this next question. Please try it out. Read it carefully. Check if the reaction is balanced or not. And based on that, you have to figure out what is the value of M. Make sure that you balance the equation here. So it should be 2 here. If you may have seen that. There should be 4 here. Correct? There should be 2 here. Right? Now if you notice, no, sorry. It's not 2. 8 here, I guess. Yeah. X should be 8 because there are 8 of them. So it should be 4 here. Correct? And it should be 4 here as well. Okay? So check. This is a balanced form. We got the balanced form. Based on that, you have to calculate this. So what we can say here is that number of moles of M will be same as number of moles of MX2, because you see the mole ratio 1:1 ratio, correct? And for every 3 moles, I'm getting 1 mole of this, which means it will be same as 1/3 moles of M3X8, right? And you can see for every 1 mole of that, we have how many moles of NX? We have 8 moles of it. So that means it will be 1/3 of, 1/3 of 8 times here, because for 1 mole, you are getting 8 moles here. So for 1/3 moles, you will get this as 8 moles. So 8 moles of NX, 8 moles of NX, correct? So now I think you know how to relate these four. So from here I can calculate number of moles of M will be equal to 1/3 into 8 into number of moles of NX. So weight of NX is given as 206 divided by number of moles. Molar mass. Molar mass of NX is 103. Okay, so that makes it how much? 2 times, so 16 by 3. Correct. So 16 by 3 moles is what will be present here. So weight of M will be equal to 16 by 3 into 56. Sorry. 56 grams. Please check. Did you get this? Ditya, did you understand, beta?
Yes, sir.
Dave, others?
Yes, sir.
Yes, sir.
Kapil, Manav,
Yes.
good beta? Right. So I'm getting this as approximately 298.6 grams. That will be the weight. Okay. Right. This ends the first part of mole concept. That is just an introduction to limiting and excess reagent. Next class, we'll discuss about all the percentage yields, principle of atomic conservation. So POAC, percentage yields, percentage purity, and all the application based on that. And then we can discuss about the solutions. What are the different types of solutions we have? How to identify the concentration of the solutions, right? So we will try to wind up the mole concept a little quickly. Got it? Because we need to spend a lot of time on redox reactions and volumetric titrations. So this, I believe that you should be able to grasp them easily. So we'll do this quickly and then we can start with redox reactions or volumetric titrations. Okay, guys?
Yes, sir.